Hello, I welcome you all in this presentation related with the subject materials processing, fundamentals and practical. And we are talking about the welding of metals. This is the second presentation on the improving the weld joint properties, because in the previous presentation we have talked about the what we can do for reducing or eliminating the weld defects and the different methods that can be used for stress relieving so that the joint performance can be enhanced. In this particular presentation, I will be focusing on how to alter the microstructure of the weld joint so that the desired mechanical properties can be obtained through the controlled heat treatment of the weld joints. Okay. So, here this is basically about the post-weld heat treatment. The different metals are based on the different strengthening mechanisms. Say for example, the grain refinement, okay, and then transformation hardening, precipitation hardening, solid solution strengthening, work hardening, and the dispersion hardening. Okay. So, if we talk of the effect of the welding heat, say fusion welding, we supply in fusion welding we supply heat, and heat leads to the heat imposes a unique weld thermal cycle along the weld line, and because of this weld thermal cycle which is being imposed, it alters the microstructure of not just of the weld metal zone, but also the zone which is next to the weld metal, that is the heat affected zone. Okay. And this alteration in microstructure is found to be significant, and which will be governing the mechanical properties and performance of the weld joint also significantly in case of the metals which are refined, which are strengthened by grain refining, which are subjected to the transformation strengthened by transformation hardening, metals which are strengthened by precipitation hardening. So, the metals which are strengthened by these three methods, they suffer very badly, they are affected very badly by the weld thermal cycle which is being imposed. Why? Because their microstructure is modified significantly when the fusion welding is performed. Okay. While the effect of the weld thermal cycle on the solid solution strengthened metal, work hardened strengthened metal, and dispersion hardening strengthened metal is there, but not much can be done as far as the post weld heat treatment is concerned. Certainly, due to the weld thermal cycle imposed, work hardened metal, they get softened significantly due to the recovery and recrystallization. But as far as the post weld heat treatment is concerned, not much can be done for this. But certainly, lot of things can be done for refining the grain structure, for altering the microstructure of the transformation hardening metals, and restoring the microstructure of the pH metals through the post weld heat treatment, so that the mechanical properties of the weld joint can be achieved in such a way that they serve the purpose. Okay. So, apart from the PWHT, post weld heat treatment, apart from altering the microstructure, it also helps in number of ways, like it helps in stress relieving, because heating is done above the critical temperature most of the time. So, stresses get relieved automatically. And sometimes when we have the hydrogen has got dissolved during the welding in certain welding processes. So, if the hydrogen is removed by heating below the lower critical temperature, then this hydrogen which is beyond the solubility limit, this will be diffusing out. So, diffusion out of the hydrogen helps in avoiding the induced cracking, cold cracking, or also it helps in reducing the hydrogen related embrittlement. Okay. So, stress relieving, reducing the hydrogen content, reducing the residual stresses, and developing the desired microstructure. These are the three main things that are realized through the post weld heating. Okay. So, as far as the need is concerned, as I have said, different metals respond differently to the weld thermal cycle which is imposed during the welding. Okay. Few metals like transformation hardening metals, what they affect, they suffer with the embrittlement or hardening. Hardening and embrittlement of the steel is so, of hardenable steel or cast irons is so high that they lose the toughness very badly. Like the steel which had the toughness of 120 or 150 joules may retain, may after the welding it may have just 5 or 10 joule, means its resistance to the impact load is very badly compromised. Therefore, it becomes important that toughness is induced. So, hardening and embrittlement of the weld metal and the heat affected zone very adversely affects the weld joint performance. If we talk of the another aspect, softening, so the steels, Q&T steels, when subjected to the welding, the heat affected zone experiences the over tempering. So, over tempering, what it leads to, the softening of the heat affected zone. Okay. Softening of the heat affected zone means the reduced strength of the joint. So, the load carrying capacity of the joint of the Q&T steel weld joints subjected to the fusion welding, that will be compromised. So, what we try to do, so these are the things related with the, like say, the hardening and softening. Softening is also observed in case of the pH metals, okay, precipitation hardening metals. So, because in the weld zone and in the heat affected zone, this reversion takes place, as I have explained earlier. Because of this reversion, the significant softening of the weld and the heat affected zone takes place. So, if the both weld and the heat affected zone strength has been badly compromised, then the joint strength will be reduced significantly. Therefore, it becomes important to restore the precipitates which have lost through the heat treatment again. Okay. So, as I have said about these two, I have already said, softening I have said. So, now the third thing is, like in fusion welding, especially in hardenable steels, steels offering the hardness of, like say, the 350 or more VHN, if the steel offering the hardness of the weld and the heat affected zone greater than this, okay, and leading to the formation of the martensite in the weld and the heat affected zone in presence of the hydrogen, which can come from the impurities or dissolved hydrogen, or hydrogen is getting into the weld zone due to the improper shielding. Then this hydrogen, what happens, this hydrogen gets diffused into the heat affected zone, and there it promotes the cold cracking, okay, cold cracking or delayed cracking. So, in order to reduce this kind of the cracking is primarily caused by the hydrogen coupled with the high hardness coming from the martensitic structure. Okay. So, if we can do little heat treatment in order to diffuse out the dissolved hydrogen, then the cold cracking tendency will be reduced. Additionally, residual stresses will be reduced, and little bit tempering of the martensite can also occur, which will help in reducing the hardness. So, the heating below the lower critical temperature can help to reduce the hydrogen content in the weld, can help in reducing the stress relieving, reducing the hardness, and reduce and tempering of the martensite. So, once all these factors happen due to the heating of the hardenable steel weld joints, then that will reduce the hydrogen embrittlement as well as the cold cracking tendency. Okay. So, here that is about reducing the hydrogen leading to the cold cracking. Now your non-uniformity in structure and properties. This is extremely common in all types of the weld joints irrespective of the metal strengthening mechanisms. So, what happens in the fusion welding, especially in the weld metal, we get the cast weld structure, cast structure in the weld, while neighboring region will have the heat affected zone. Okay. This heat affected zone is usually coarse, okay, both the sides very coarse grain structure, or that we can say CGHAZ is formed both the sides. So, the cast weld structure, coarse grained heat affected zone. Apart from that, depending upon the metal system, like it can have the martensite or perlite in case of the hardenable steels, it can experience complete reversion in case of the pH metals, or it can in case of the work hardenable metals, it can due to the recovery and recrystallization, it can lose its hardness completely. The thing is this, right from the base metal to the heat affected zone and the weld metal, significant variation in structure, microstructure is observed, and because of this microstructural variation, what happens, like say this is the weld zone, so we can get significant hardening like this, like this. So here this is the heat affected zone which is harder, weld zone is further harder. Okay, this is HH at both the sides. So this is the one type of arrangement. Another one here, we can have significant drop in the hardness. So weld metal is little stronger, but the HH is significantly weaker. So so these are the two typical examples. In here one case hardening is taking place, another softening is taking place. This is typical example of the hardenable steels, and this is typical example of the pH metals. Okay, so this kind of the non-uniformity in structure leads to the non-uniformity in mechanical properties, and it leads to the formation of the weak zones in the HZ, especially if the softening is taking place, or it can also occur, it can also lead to the loss of toughness and embrittlement if in case of the hardenable steels. So what we can do, we have to restore the structure, whatever it had, let us bring in that first, and so that our mechanical properties are realized. Okay, mechanical properties are restored, and for that what we need, we need to realize the desired microstructure through the controlled post weld heat treatment. So again, that will depend upon the kind of type of metal, whether it is a heat treatable steels, or it is the pH metal, or the metal has been only strengthened through the grain refinement. Okay. So, as per the metal, we try to choose the suitable heat treatment cycle, so that the desired structure of the parent metal can be restored to have the desired set of the properties. So, heat treatment, when it is done, it helps in improving the toughness through the heat treatment of the weld joint of hardenable steels, like inducing the toughness through the heat treatment, like tempering, or improving the corrosion resistance. This is realized because of the homogeneity of the composition, uniformity of the microstructure. So that in turn helps in improving the corrosion resistance and the thermal. When the heat treatment is done, because of the reduced yield stresses, locked in strain is relieved, and that in turn helps in stress relieving. Okay. So the post weld heat treatment helps in multiple ways, like it can help in reducing the hydrogen content, developing the desired microstructure, improving the corrosion resistance, and stress relieving. So these are the multiple benefits that are realized through the post weld heat treatment. Okay. So as far as the need is concerned, I have already explained a lot. All the, so because of this heterogeneities in microstructure and mechanical property, non-uniformity in mechanical properties, it becomes important that the structure is realized, so that the base metal property, so the proper. Okay, I'll repeat it once again. So we have seen that there is a lot of heterogeneity in microstructure, and that in turn results in the heterogeneity in properties as well as the anisotropy, and this primarily comes from the heat unique weld thermal cycle which is imposed during the welding. So unique weld thermal cycle causes the structural variation, heterogeneity in structure and properties. Okay. So, like say this happens especially when the all in the zones which are heated above the critical temperature or above the Solvus temperature in case of the PS metals. Also, this kind of the changes are observed in the parent metals which is heated above the recrystallization temperature. Since the weld thermal cycle of the each location is different, and therefore we get the variation in the microstructure, and most of the time the structure which is developed in the HZ and in the weld metal zone, that is undesirable, and this can promote the weld thermal softening in of the heat affected zone and coupled with the mechanical properties, and because of this heterogeneity in structure and non-uniformity in mechanical properties, now we get the poor mechanical performance. Therefore, it becomes important to do the post-weld heat treatment. So, what heat treatment does is it primarily modifies the structure. Okay. So, this modification in structure can be there in form of the phase structure. For example, if steel is having the martensite in the weld and the heat affected zone due to the typical weld thermal cycle imposed and leading to the embrittlement and loss of toughness, then the tempering will help to modify the untempered martensite which is produced. This will be leading to the formation of the tempered martensite. Okay. This is one. Similarly, if the grain structure is realized, and phase structure also can be like, if there is a solid solution, then through the heat treatment we can have the suitable kind of the precipitates in order to impart the desired strength. Metals which are primarily strengthened through the grain refinement, heat affected zone experiences significant grain coarsening. Okay, very coarse grain structure. So, if we impart the desired thermal cycle, that can help in refining the grain structure and improving the properties. So, we can design the heat treatment suitably so that the phase structure as well as the grain structure is modified in order to realize the properties as per the need. So, what heat treatment does is it modifies the structure. Okay. It also helps in relieving the stresses by reducing the yield strength to relieve the locked in strain. It also helps in improving the homogeneity of the structure and properties, and that in turn will be eliminating the anisotropy. So, all these aspects actually help in improving the performance of the weld joint. Okay. So, when we achieve the desired microstructure, stresses are relieved, we get the homogeneity of the structure and properties and try to eliminate the anisotropy. All these factors in totality help in improving the performance of the weld joint. So, what are the properties that can be altered through the controlled heat treatment is mechanical properties can be changed in terms of the tensile strength, yield strength, ductility, toughness and the hardness. Microstructure can be refined, and we can also realize the desired set of the phases through the controlled heat treatment in order to achieve the desired mechanical properties. Similarly, the stresses can be relieved through the annealing or the tempering in order to reduce the residual stresses and improve the dimensional stability so as to reduce the cracking tendency. And when the heating is done at a higher temperature, so this also helps in improving the dimensional accuracy as the dimensions are stabilized even after the heat, even after the welding, and once the heat treatment is done. During the machining, there won't be any dimensional variation due to the distortion related thing. Okay, so steels respond very nicely to the thermal cycles which are imposed. Like say initially we may have ferrite and pearlite depending upon. So, when we do the heat treatment, it converts into the austenite. This austenite, depending upon the cooling rate imposed, it can produce coarse pearlite, it can produce fine pearlite, it can lead to the formation of the bainite, or it can lead to the martensite. So, all are of the different kind of the microstructure, and different, all these phases offer the different kind of the mechanical properties, and that in turn helps in realizing the desired mechanical properties of the weld joint. So, that is the beauty of the steel, where by for a given composition, by imposing the thermal cycle, we can realize the desired phases to obtain the desired mechanical properties. So, once the steel is heated to the austenitization condition and homogeneous austenite is formed, depending upon the cooling rate, we can get the desired phases. Say coarse pearlite is realized through the slow cooling. Okay, during the annealing. This helps in eliminating the embrittlement and inducing the softness, okay, increasing the ductility, increasing the percentage elongation. But certainly this will be happening at the cost of the yield strength and the hardness. Normalizing, what it does, it produces the very fine grain structure, okay, that helps in increasing the strength of the steel weld joints. Certainly it relieves the residual stresses, it brings the dimensional stability, okay, and this is realized through the higher cooling rate, okay, higher cooling rate. About this we will be talking in the next slide. Okay. So, when we have got the like homogeneous austenitic state, then very rapid cooling, very rapid higher cooling rate will be resulting in the transformation of austenite into the martensite. Okay, and this martensite will be resulting in the increased yield strength and increased hardness, but certainly at the cost of toughness and ductility percentage elongation. Okay. So, if this is done, then see the weld joints in hardened condition will not be used because of the reduced toughness and ductility. So, followed by the tempering, so that the suitable degree of the toughness is induced and the residual stresses are relieved. Then if we can also go just for the stress relieving by choosing the suitable heating temperature, so that the desired reduction in the stress residual stress can be realized. So, how to design the heat treatment? So, there are three aspects, and the typical thermal cycle we can see here. We have to heat the component or the weld joint, followed by austenitization to achieve the homogeneous austenitic state. This is done depending upon the lower upper critical temperature, say for the heat treatment like annealing, normalizing and hardening. What we do? We heat the component depending upon the carbon content to the temperature 30 to 50 degree centigrade above the upper critical temperature. Then we hold it at that temperature for homogeneous austenitic state, for attaining the homogeneous austenitic state. Thereafter, we impose suitable cooling rates, slow cooling for annealing, for little faster cooling for normalizing, and further higher cooling rate for the hardening purpose. This is the typical thermal cycle which is imposed. So, what will be the temperature up to which we have to heat? We have to identify the upper critical temperature. Upper critical temperature depends upon the carbon content, say in case of the carbon steels. So, if say this is the a part of the iron carbon diagram. So, iron carbon diagram, we can see if the steel is 0.4% carbon steel. So, we have to see draw vertical line like this and we will get the upper critical temperature. So, we heat it 30 to 50 degree centigrade above the upper critical temperature to attain the homogeneous austenitic state. Okay, once this is realized, so this is the heating temperature that is identified based on the iron carbon diagram. Then based on the composition, we have to see that we hold it at that temperature for long enough, so that the homogeneous austenitic state is achieved. So, as per the identified austenitizing temperature, we have to see that it is held at a higher temperature for long enough, so that the homogeneous austenitic state is attained. If it is the alloy steel, then it will take longer to attain the homogeneous austenitic state as compared to that of the plain carbon steel. Okay. Once we have attained the homogeneous austenitic state, then we have to see that what are the conditions as per the kind of the composition of the steel. We have to see that what kind of the cooling rate is to be used for annealing, normalizing and hardening purpose, and that is based on the triple T diagram or CCT diagrams. That is what we will be seeing in the next slide. So, if we see here, there are three things. One is the heating to a particular peak temperature, that is based on the 30 to 50 degree centigrade above the upper critical temperature. Then soaking, as per the composition at a higher temperature, we try to find out like how much time it is to be done, so that the homogeneous austenitic state is attained, followed by rapid cooling. Okay, rapid cooling, moderate cooling or slow cooling as per the kind of the heat treatment to be performed. So, these are three steps: heating at peak temperature, soaking, followed by the cooling rate. So, if we see that if the austenite is held at a higher temperature, at a constant temperature, say which is much higher, around say 700 degree centigrade, then we get the coarse perlite. If it is held at a little lower temperature, then we get the fine perlite. If it is held at a further lower temperature, then we get the coarse bainite and fine bainite. And if it is held directly at the temperature below the temperature, then we convert the austenite into the martensite plus austenite or only martensite as per the temperature at which it is being placed. Then, but this is about the isothermal transformation diagram. This just gives the idea the kind of phases which will be formed when the steel in austenitic state is kept at a particular temperature. But when the steel is subjected to continuous cooling, then what we get? On slow cooling, we get the coarse perlite. On little faster cooling, we get the fine perlite. On further faster cooling, we get the mix of martensite and perlite. Further higher cooling rate, which is just tangential to the nose of the CCT diagram, this gives us the martensite, and further higher cooling rate also gives us the martensite only. So, depending upon the kind of the phases that we are looking for, if it is the annealing, then we will be imposing the low cooling rate. If it is normalizing, little higher cooling rate. And if we are looking for the high strength and high hardness, then we will be going for the martensitic transformation, means austenite to martensitic transformation. But when this austenite to martensitic transformation happens, okay, during the hardening especially, this leads to the significant increase in the hardness, but at the cost of toughness, at the cost of the percentage elongation, and that makes the joints not usable, not suitable for many applications where the impact conditions exist. So, what becomes important, like do the tempering of the weld joint. Okay. So, after hardening, you see, followed by rapid cooling, then steel is joint is tempered. So, this tempering can be done in the range of temperature, say from 200 to 600 degrees centigrade up to the below lower critical temperature. Okay. When this tempering is done, what we get? We get the increase in the toughness, increase in percentage elongation, but at the cost of the hardness. Okay. Now, when the joint is hardened directly, we induce the lot of tensile residual stresses at the surface, and that can promote the cracking. Okay. So, what we do in order to avoid this kind of the undesirable effects, what we try to do is we do the tempering, so that the residual stresses are minimized, and the excessive hardening is also minimized by reduction in the hardness, and therefore tempering becomes important. So, in case of the, say, the tempering is done at a different temperatures of the weld joint. So, steel, say hardenable steel has been, just after the hardening, it has attained the 60 HRC hardness, and if we go for the tempering at different temperatures, then our hardness will keep on decreasing. Okay, in case of the carbon steels. But in case of the alloy steels, we get the secondary hardening, because at this stage we find that certain alloy carbides are formed in the steel at a higher temperature. So, that is why initially in alloy carbides, initially there will be drop in the hardness, but at a higher tempering at a higher temperature will be resulting in the again secondary peak that comes due to the secondary hardening. On the other hand, so but here our idea is to have the marginal drop in the hardness coupled with the increase in toughness in order to have a good combination of the hardness and toughness. So, what happens when the steel is subjected to the heating to the higher temperature during the tempering, this induces the toughness, increases the toughness, say just after the hardening it has like 20 joule, and if you go for the tempering it can be increased significantly 150 or 180 joules depending upon the kind of the metal. So, the tempering helps in restoring the toughness, inducing the ductility, and reducing the residual stresses depending upon the tempering temperature which has been selected. Okay. Now, we will be seeing the another kind of the metal systems like pH metal joints. Precipitation hardening metals, like when these metals are subjected to the welding, these precipitates are present, but when the zones which are in the heat effect, the region which is next to the fusion zone, that will be experiencing significant reversion or even formation of the precipitate free zones, and this will be causing significant softening in the heat affected zone, because the weld metal composition we can adjust as per the need and properties can be realized, but not much can be done with the heat affected zone. So, we need to do something in order to avoid this so kind of the softening of the heat affected zone. This softening is attributed not just to the reversion, but also the grain coarsening of the heat coarsening of the grains in the heat affected zone. So, this in turn degrades the strength significantly and also promotes the corrosion or reduces the corrosion resistance. So, it becomes important to restore the precipitates through the suitable heat treatment cycle, which will be involving the solutionizing, quenching, followed by aging. So, what we do in this case, depending upon the kind of metal system we have, like say this is the kind of the alpha zone, and here we have the different lines corresponding to the different phases. So, here say the metal of this composition heated in the homogeneous solid solution condition, then it is quenched rapidly, then reheated again. So, the solutionizing helps in solutionizing is step which helps to dissolve each and everything in the solid solution, followed by rapid cooling, that is called quenching, in order to attain the supersaturated solid solution, and then as per the and followed by aging. So, if we after development of the supersaturated solid solution, it can be reheated to the high temperature for artificial aging during the T6 heat treatment for development of the precipitates again, hardening precipitates again, or we can leave it at a room temperature for the natural aging. The natural aging takes very long in order to restore the properties and the microstructure as compared to the T6. So, now I will summarize this presentation. In this presentation, basically I have talked about the, the various principles associated with the post-weld heat treatments for restoring the structure and properties, so that the joint properties or the performance of the joint can be enhanced. Thank you for your attention.